I'm really glad to be here. I haven't been to Vail before. It's beautiful. It took some doing to get me here this morning, but I'm really glad to be here to talk to you about the scientific search for life elsewhere in the universe. So I'm an astrophysicist. Most of my work in my career was done looking for exoplanets. That means planets that orbit other stars. When I started doing that, we knew of about 20 planets orbiting other stars. And now we know of over 6,000 planets orbiting other stars. It's been really amazing. And I've sort of shifted my research focus because now we know these things are out there. Could there be life on them? And so I take an astrophysicist's perspective of trying to find other examples of life elsewhere in the universe. A lot of astrophysicists do this looking for microbes. We might be looking for microbes on Mars or hints of metabolism in the atmospheres of planets orbiting other stars. I'm one of the few that actually wants to jump all the way to the end, not just the microbes or the plants or something, but find an intelligent species, something that could do something with engineering, maybe build a radio transmitter, maybe build spacecraft or something that can go throughout the galaxy, and find another intelligent species and see if they're out there in the galaxy. Now, when I say that, I'm sure everybody has some images in their minds about what I'm talking about. It's great. If you're in science like me with a PhD and you're on an airplane, and someone asks, what do you do, what do you study? Normally, you've got to figure out how to describe what you work on in a way that will make sense, because it's usually extraordinarily technical. But when I get asked that on an airplane, and I say, I look for life elsewhere in the universe, I don't have to dumb it down at all, because that's really what I'm doing. It's great. It's a lot of fun. But that's because we all have these ideas about what we might find out there. So if I say the scientific search for extraterrestrial intelligence, what are some of the images that come into your mind about what I'm looking for? Where do these images come from? What comes to your mind? You got ET, what was that? Radio waves? Okay. Yeah. So let's take a look at some of those images. So here are some aliens from television is it gonna work? Uh-oh. There we go. Here's some aliens from television. Anyone recognize these aliens? Yeah. Is this what aliens are gonna look like when we finally find them? Probably not, right? I mean, these look suspiciously like people with paint on their faces. Science fiction gives us aliens, but really science fiction tends to be stories about people. This episode of Star Trek is about racial and ethnic strife. And so, to make the allegory really clear, they're just people with, funny colored faces. And so, when we get our ideas from science fiction about what we're looking for, we have to keep in mind that the aliens are serving narrative devices that are popular that make you want to watch it. They're not necessarily a scientific analysis of what we might be looking for out there. Here's another alien. This one came up. Isn't this a great alien? He loves children, he loves life, he's physically fragile, highly intelligent. Because this is, a Spielberg feel-good movie, and so the alien has to conform to that. Now, this doesn't look much like a person, but if you think about it, E.T. actually does, right? He's got a head, he's got bilateral symmetry, he's got eyes, ears, he's got a mouth, he can talk. He's got two, arms, legs. He's just a funny-looking human. We don't think that real aliens will actually conform to the human body plan. So again, this is not a serious attempt about what aliens might be like. Now, aliens apparently in film, they've got to interact with, little blonde children. Here's another one. Now, this is a different genre of film. We're into horror, action, and so now our alien's got to be big and ugly because you got to know it's the villain. It wouldn't make sense if this alien was the one stalking her through the sewers and killing people, right? That wouldn't make narrative sense. Now, when I say the search for extraterrestrial intelligence, someone said radio waves. Here's an image that comes to my mind. Can I get it? There we go. How many people have seen this movie? Great. This is Contact, based on a novel by Carl Sagan. The character here, I should say this film Contact is one of the most scientifically accurate science fiction films. Because except for the part where she actually finds aliens, everything in it is accurate on how things really work, except the headphones. You're not actually allowed headphones connected to Wi-Fi laptops. because the radio waves mess up the telescope. So that was a little bit of poetic license. But other than that, this is extremely accurate. In fact, it's so accurate that this character, Ellie Arroway, is based on a real person. It's based on Jill Tarter. She's a hero of mine, and her name's going to come up later. So remember that face. All right, sometimes it works, sometimes it doesn't. Not working now. Oh, here we go. Okay, so let's think about, we often say, like, we've been looking for alien, people have wondered for millennia. They've looked at the sky and wondered, are we alone? And that's not really true. So, we like to, when we look for exoplanets, we like to show this quote by Albert the Great, one of the doctors of the Catholic Church, who said, "Do there exist many worlds, or is there but a single world? It's one of the most noble and exalted questions in the study of nature." And it makes those of us that look for exoplanets feel very important. We like to show this. But what Al was really thinking about was the heavens. And to most people through most of history, the heavens have been where the divine things are. And so when they think about consciousnesses in space, they're not thinking about ET. Right? They think about angels, they think about God, divine beings. The heavenly and the divine were synonymous for a long time. When that all changed was with Copernicus. Copernicus took seriously the idea that the Earth orbited the sun just like the other planets, which meant the other planets were just like the Earth. And so suddenly the planets were not gods or where the gods lived or divine, they were very terrestrial. And Galileo reinforced this with his telescopic observations of Venus and of the moon. And he showed they had very terrestrial features. Oh, I'm sorry, one more. Things are now advancing without me. Okay, so before Galileo and Copernicus, we had these ideas. One of the first people that we know of to think seriously, to tell a story where they were not divine beings was Lucian of Samosata, who was Greek, and he wrote a satire of Greek mythology, people who took the gods too seriously, like Mount Olympus and all that, and thought it was real and not an allegory. And so he told a story about people who go to the sun and the moon and meet the spider people there. This is sometimes called the first science fiction story. But he was being silly. It was obviously silly that they wouldn't be divine beings up there, that they'd be beings like ours. Okay, we're going to try to go forward. Giordano Bruno, was a heterodox monk who took Copernicus's teachings very seriously. And he asserted, without any evidence, that there are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets in our system. He was thinking about the stars, and he was claiming the stars were other suns, and they had planetary systems. We see only the suns because they are the largest bodies and are more luminous, but their planets remain invisible to us because they're smaller and non-luminous. This is exactly correct. He's making a great guess. The countless worlds in the universe are no worse and no less inhabited than our Earth. Again, he's just wildly guessing here. This heresy was called the plurality of worlds, and for his trouble in 1600, he was burned at the stake for that and many other heresies, and became a martyr to free thought, and he continues to be a martyr to freedom of thought and free thinking, if not the scientific method. We're going to fast forward a bit. Percival Lowell was a self-made astronomer who built an observatory and started to track what he thought were the seasons and the industry of the Martians, building canals across the surface of the planet. And he tracked them from his observatory. And he wrote books like Mars and its Canals, and later books about life on Mars, about what the Martians were like. He thought he could infer all sorts of things about their civilization from his observations. And so for the first part of the 20th century, until NASA's Mariner missions went to Mars, it was still an open question if there might be life on Mars. And in fact, some of the engineers building those spacecraft used Lowell's maps to guide where they would go, and would have grown up learning that there was life on Mars. All right, there we go. The search for extraterrestrial intelligence as a scientific venture starts in 1959. These two fellows, Cocconi and Morrison, came to a startling realization and immediately wrote a scientific paper that got everyone thinking about it. It was really catalytic. The idea was that aircraft radar and radio transmissions that had been perfected in the Second World War were now powerful enough, and our ability to detect those signals was now powerful enough, that if we put our largest, best transmitters around a planet on another star, we could detect them here on Earth. That's how good radio communication had become. Which means that if there are intelligent species out there in the cosmos around other stars, and they have radio transmitters, we could detect it. That's really profound. This was no longer an academic discussion. This was something we could test. Someone else had exactly the same idea, Frank Drake. He was a young radio astronomer, Harvard-trained astrophysicist in West Virginia at the National Radio Astronomical Observatories. And at around the same time, he began Project Ozma, named after the Princess of Oz, because he was thinking about the books he read as a child about fantastic creatures that live far away. And he thought maybe we can detect them. And so he began a program to scan the skies for radio waves. And so this is where it begins, this scientific effort to find intelligent life in the universe. So that was in 1960. Cocconi and Morrison's paper inspired a lot of thought. And by the 1970s, NASA was ready to jump in with both feet, and it began its SETI program, the Search for Extraterrestrial Intelligence. The idea was that they were going to do a huge radio survey, check every star, every frequency, and see if anything is out there. 1978, budget cutting was a big thing. William Proxmire liked to find silly-sounding government programs and then grandstand about how he was, cutting the pork and keeping the deficit down by zeroing them out. He gave SETI the Golden Fleece Award for fleecing the American taxpayer. And the program ended. Now, that wasn't a very nice thing to do. The newspapers ran a blurb. Here it says, Proxmire suggested that the project be postponed until the federal budget is balanced and income and Social Security taxes are reduced to zero, or for a few million light years, whichever comes first. Which is especially galling because light year is a unit of measurement, not of time. And so this is doubly galling to those of us that read this today. Carl Sagan worked on him and eventually got him to change his mind. He agreed that that was not a nice thing to do, and he favored refunding the program. And so they rechristened it the High Resolution Microwave Survey, and they got it going. And the person that was going to lead that project at NASA was Jill Tarter, which is how she got into the field. And for the rest of her life, she became an advocate in this field and led the way. The joke on Capitol Hill was that HRMS didn't really stand for the High Resolution Microwave Survey. It stood for, he really means SETI. Like they were trying to hide what it really was. They just can't help themselves. In 1993, Richard Bryan, the senator, introduced a last-second amendment to end all SETI funding. And at that point, NASA learned its lesson. And since then, NASA has given almost no money to the search for extraterrestrial intelligence. It's pivoted to finding, as Jill likes to point out, stupid life. Microbes on Mars? Absolutely. We're going to see things in the seas of Enceladus. Let's send a mission. But hardly a penny for intelligent life that we might find. So Jill had to become a fundraiser. And so out in California, she, Carl Sagan, and many others worked tirelessly to get philanthropic funds. The movie Contact actually grew out of an effort to convince people in Hollywood that it was worthwhile. The plot of Contact is how unjust it is that SETI is not being funded, and about a billionaire who funds it, and it succeeds as a result. Here we go. Oh, Richard Bryan's quote, "This hopefully will be the end of Martian hunting season at the taxpayer's expense." Not even looking at Mars. Oh, okay. So in 1995, one of the founders of Hewlett-Packard, Barney Oliver, who had done a lot of work in the field, died and left a substantial share of his estate to found the SETI Institute. So this is a nonprofit research institution in Mountain View, California, and it's become kind of synonymous with this effort because it's the only place, or had been for a long time, the only place where this sort of work was done. In 2001, Microsoft's Paul Allen donated over $30 million to construct a new telescope array. In 2015, another Silicon Valley billionaire, Yuri Milner, founded a $10 million a year project called Breakthrough Listen, centered at UC Berkeley, to continue the search, mostly in the radio. And just recently, Franklin Antonio, a co-founder of Qualcomm, bequeathed $200 million to fund the SETI Institute. And so where NASA wouldn't fund it, philanthropy has really stepped up, mostly to do the radio SETI that we've already talked about. But the field is broader than that. Radio SETI has attracted a lot of attention because in many ways it seems like the best bet. But almost as soon as the field started, there started to be some other ideas. So let's talk about some of these ideas that go back to the founding that maybe you've heard of. The Fermi paradox is a common one. So it's named after a conversation Enrico Fermi, the Italian particle physicist, had at a national laboratory. Over lunch, he said, "Where is everybody?" And there had been these UFO sightings and things, and people were thinking about whether there could be aliens. And everyone understood what he meant. If they were really out there, they'd be all over the Earth. We would notice them all the time. So if there are aliens out there, why don't we see them? Why aren't they here on Earth right now in a really obvious way? It's called the Fermi paradox. It's not really a paradox, formally. It's also not even really Fermi's. He just asked the question, and a journalist connected his name to the idea. The idea was actually formalized much later, in the 1970s, and got the name the Fermi paradox. And it's about why they're not here on Earth today in a really obvious way. It's not really a problem. People often bring this up as some great puzzle to be solved, but it really isn't. Oh, but let me maybe illustrate to you why the Fermi paradox works. So this is the galaxy. And you can say, well, maybe there is life out there, but why would it be here? It's a huge galaxy. How is it they could get all the way from over there to over here? Maybe space travel is just really, really hard. But let's do a thought experiment where we just use chemical rockets. Maybe in 10,000 years we can do this. We can build a big rocket, send it to another star. And it takes 10,000 years to get there. Stars are really far away. But, maybe we've figured out how to do hibernation by then or something. This isn't warp drive. I'm not breaking any laws of physics with this thought experiment. This is a plausible trajectory for the human species or another species. So this is a simulation we did. What would happen if, and you'll see these little bright things and red dots appear. Those are stars where someone has sent a ship nearby and set up a settlement. And people live there and build more ships and send them out. And so the amount of time you're seeing go by is millions of years in this simulation. And the point is that you get exponential runaway growth because each settlement that you set up can build more settlements. And so even without warp drive or Star Trek, the number of settlements just grows exponentially. And the galaxy spins and mixes and helps carry them all over the place. And in the end, the galaxy gets filled with settlements. So it's a naive, simple numerical model. We don't know if things really work this way. But that's the illustration of the Fermi paradox, that once settlement gets going through the galaxy, it should happen pretty quickly. So why aren't they here? Where is everybody? Well, for one thing, the solar system's taken already, right? We're already here. Maybe they've been here and didn't stay. Who knows? Maybe it's just really hard to travel among the stars. Sometimes people say, well, the Fermi paradox is, if they're really out there, we should have heard from them by now. We should have heard their radio waves by now. But that can't be what Fermi meant, because Fermi made his question in 1950 before we'd even started looking. So sometimes if we want to talk about why haven't we found anything yet, I'm trying to advance the slide here. Here we go. So that's not what Fermi meant. Sorry. Sometimes we talk about the great silence. The great silence. Why is the universe so quiet? Why aren't there radio waves coming from all of these other settlements out there? Or an eerie science, like it's some sort of big mystery to be solved. But those of us in the field understand this isn't actually a big puzzle. The amount of frequencies we have to check is billions. The amount of directions we can point our radio telescope is billions. We can't check every part of the sky at every possible frequency. We have to guess where we might be looking. And so Jill Tarter liked to argue, let's say you're looking for fish in the ocean. You don't know where to go. You don't know if there's fish in the ocean. The amount of searching we've done for radio waves is analogous to taking a drinking glass and dipping it in the ocean and seeing if you caught a fish. And if you don't see the fish in that glass, it'd be silly to say the oceans are sterile. There are no fish at all in the ocean, because the oceans are actually teeming with fish. We've searched so little so far that we actually can't say anything about what's out there. I recently did this calculation. Now that we have Breakthrough Listen and these other philanthropic efforts, we're up to a hot tub's worth of water. And you know, if you're looking in the right spot, near a coral reef, near the shore, if you've guessed right, that volume of water might be likely to have a fish. So I feel like if we can be intelligent about where we point the telescopes and what we're looking for, we have a really good chance of finding something these days, which is very exciting. Let's get back to Frank. So Frank Drake, here he is next to his famous equation. Anyone heard of the Drake equation? It's been called one of the most famous equations in physics. It comes up a lot. When this field was young in 1961, he wrote this equation down on a board with a bunch of other scientists, including Carl Sagan. Some Nobel laureates were there. And he said, let's figure out if it's worth looking for aliens. So n, that number on the left, that's an estimate of the number of aliens out there that we could detect today. Now, how do you estimate something like that? Physicists like to do this. It's called an order of magnitude problem. He said, well, there can't be more than there are stars in the galaxy. So every star could potentially have such a place. We multiply that by FP, that's the fraction of those stars with planets. Multiply that by the number of planets like Earth around each of those stars, the fraction where life forms, the fraction of that life that grows brains and radio telescopes, the fraction of those that are signaling, multiplied by how long they signal, because if they only signal for 5 minutes, we're not likely to find them. And there's the estimate. And they didn't know any of these numbers when he wrote it down except the first one. They had to guess. They had to guess what every one of those numbers were. But even when you put in pretty pessimistic numbers about how many planets might be out there, about how often life might form, that first number, the number of stars in the galaxy, was 200 billion stars in the galaxy. You multiply by that by some pretty small numbers, you still get that there should be something to find. So this equation doesn't prove there's something out there to find. It's just a thought experiment. But it does justify the search. It says it's very plausible there's something to find. It's worth looking for. And that's one of the things that makes it so galling that, that Congress cut funding so often, because it's an important question. So I said there were other ways to look that haven't had much work done on them, because the billionaires tend to like to fund the radio telescopes. But as soon as Cocconi and Morrison published, the future Nobel laureate, Charlie Towns, who invented the laser, said, you know, lasers would work really well, optical lasers. You don't need to use radio telescopes, you can use regular light. And in fact, we do in our fiber optic cables. And NASA is moving towards communicating with our deep space probes using lasers. Maybe that's the communication of the future. Maybe that's what we should look at. Not a lot of work has been done on this. Some has. There are some upper limits we have, and a little more. But this is another direction we could look. Around the same time, another astronomer, well, an engineer, where is he? Here we go, Ron Bracewell, argued radio waves and light are really slow ways to communicate. You can't get very much information across the cosmos with radio waves compared to sending something physical. So he argued that they would send probes that would just hang out in the solar system, and we could communicate with those. That if you're willing to wait long enough, sending probes is the way to go. There's another, and there are lots more ideas. In the question and answer, you can ask me about all the other ways we think we might find these things. This is one of the things we do at Penn State, is try and broaden the search to other things so that we don't miss the signal, miss N, because we were not just tuned to the wrong frequency, but looking at the wrong kind of light. But let's get back to Frank and radio telescopes. We've been looking for a long time, but there's this problem of how you know you've succeeded in finding what you're looking for. I'll give an example of that problem. This is called the wow signal. Anyone heard of the wow signal? All right. One of the radio telescopes that did a big search, the longest running search, was at Ohio State, called the Big Ear, really big radio telescope. And for decades, they had a program where they went and scanned the skies for radio signals that might come from alien civilizations. And they recorded on these charts how strong the signal was. And they were looking for a particular pattern that would indicate that the signal that they had seen had really come from space and was quite bright. And they used numbers, 1, 2, 3, to say how bright the signal was. And so you see there's all these 1s and 2s. That's just noise. That's normal background. But one day, at just one frequency, which is not what nature does, just one frequency. It got really bright. It got so bright that they ran out of numbers and the computer had to resort to letters to describe how bright the signal was. And the pattern, not the EQU, those are just made up numbers by letters by the scientists, but what those letters are telling you is it got much brighter and then much fainter, and that pattern tells you it really came from space. It wasn't from Earth. So we circled it and said, wow, right there in the margin, like that's what we've been looking for. We finally found what we wanted. But then what? They went and pointed there again. Lots of people have pointed at that part of the sky again, and we've never seen it happen again. So now people scratch their heads like, I guess it's not good enough just to say, oh, I think I found something. You have to be able to follow it up. You need some kind of program where you can say, I found it, other people see it, you have to confirm it. If you're going to do science with these things, they have to be repeatable, and that makes this whole thing a challenge. And what makes it really challenging is that in the meantime, people are going to ask you, have you found anything interesting? And if you're like, yeah, wow, I found this signal, and it might be from outer space, you know what the media is going to say, right? So most of us see this as an interesting maybe, but when we talk about it with the media, they're like, scientists find aliens. And so that communication is what the rest of this talk is about how we, as serious scientists doing this search, communicate with the public and with the press about what we're doing without sensationalizing it. So when Frank wrote this equation down, they didn't know what the value of any of those numbers were. And we've actually made a lot of progress since then on two of them in particular, these two. What fraction of stars have planets and how many planets are around each of those stars? It turns out the numbers that they put in 1961, guessing, were correct. Virtually every star has a planet. And the typical number of planets like the Earth, somewhere between 1/4 and 2. Basically it's like 1. Just about every star in the sky has a planet like the Earth. Maybe only 1/4 of them do. But that's close enough to 1 that means that there are tens of billions or hundreds of billions of planets like the Earth out there. Now, that doesn't mean they have water on them. We don't know that. But planets the size of Earth that could have water. How do we know something like that? How did we learn something like that? Well, NASA to the rescue. So out there, all those stars have planets. But most of the planets orbit the stars in a way that we would just never notice. So if you're Earth, here's the star, and the planet goes around. It's very hard to tell. But sometimes, randomly, some of those systems are lined up with the Earth. Just by chance, some of them have to be. And every time the planet goes in front of the star, it'll block some of the starlight. Every single time it goes around. So here, that chart shows the brightness versus time. The star's bright, and then when the planet goes in front, it gets a little dimmer. Now this is greatly exaggerated. Planets are really small, stars are really big. It only gets not 1% dimmer, but 1% of 1% dimmer. It's very subtle, very hard to detect from the ground, almost impossible. But NASA launched the Kepler Space Observatory. And the Space Observatory stared at 100,000 stars like the sun for 5 years, because the planets like Earth go around once a year, and looked for these subtle little dips as the stars get dimmer just a little bit and then brighter again. And then a year later they do it again, and a year later they do it again. It's a very subtle experiment. It took a huge amount of work. And what it revealed, it's just 100,000 of these things. And I just want to remind you, this is what it looks like. When the planet goes in front, keep this in mind, we'll need it later. The star has some brightness. It gets a little bit dimmer, again, greatly exaggerated. These dips are just 1% of 1%. And then it goes back up again. And now we know they saw so many of these that when you multiply by all the ones we must have missed because they don't happen to line up, virtually every star has a planet. That's amazing. And that really helps justify the search for life out there. Because it could have been, planets were so rare it's not worth looking for. This validates the searches that Frank Drake has been doing, that he did for a lot of his life, and that Jill Tarter's been doing. Okay. There's another way we might go finding technology out there. And this is one that I've spent some time on. The idea, I could tell you all about it, but having never seen alien technology, only having thought about it, I'm not an expert on alien technology. So I'm going to hand things over to a true expert on aliens and alien technology, Captain Jean-Luc Picard. All right, this is a fun episode. I like this. I love Star Trek. My kids and I are watching, going through all of them. But everything about that's wrong. And I don't know anything about Dyson spheres, but I do know none of that is possible. So here's what it looks like. This is the inside surface of the sphere when they fly inside. And it's got like continents and cities and stuff like that, because people built this giant sphere around their star. But it turns out that's like physically impossible. I mean, for one thing, you'd fall off the inside of the sphere. In Star Trek, they have artificial gravity. That's impossible. It's common in science fiction, but that's because it's really hard to do zero-gravity stories on a TV set. And so they say, oh, we do artificial gravity, it's fine. And, just say it exists, and it does, right? It's television. And so this is another example of the contrivances of the narrative affecting what we expect we might see. But the idea of a Dyson sphere is actually not that there'd be a sphere like that. Freeman Dyson, who was a great physicist, his actual idea, I also Googled Dyson sphere to see what people had drawn and what these things might really look like, and got these very fanciful illustrations. I'm not exactly sure what's going on in all of these. I'm not sure the artist had, this kind of looks kind of pretty or something like that. The idea, though, is actually much simpler than building some sort of huge structure. Why would you do that? It's just that given enough time, you're going to need a lot of energy. And if you're out in space, it's hard to get energy in space, right? You can't go drilling for oil out there in outer space, right? And so there's a lot of energy to get in space coming from stars. Stars just give you all the energy you want. And so if you build solar panels on your spacecraft, now you have energy. If you have a lot of spacecraft, a lot of space stations, they're going to need a lot of energy, and all of them will have solar panels. And if you have enough of them, they might start using a significant amount of the star's light. So give us 10 million years putting satellites out in space, and it might get really crowded around the sun. So maybe a better idea is something like this. They don't all have to be the same shape. They don't have to be regularly spaced like this. But just imagine that around a star you have so much spacecraft that they block a significant amount of the light. So that's the idea. Has that ever happened somewhere in the galaxy? And what Freeman Dyson figured out in 1960 was that if it had ever happened in the galaxy, we'd be able to tell. This would actually be kind of obvious, and I'll explain what his idea was later. But more recently, and connected to Kepler, is the idea that NASA might have been able to find one of these things. Right before Kepler launched, an astronomer pointed out that the Kepler satellite was so precise that not only could it tell a planet was going in front of the star, it could sort of almost tell what shape the planet was. Now that's kind of silly, right? Planets are spheres. Obviously it's going to be round. But he said, well, what if, someone's built a big space station or something? There's no reason they'd make it round. Maybe it's some other shape. So he just picked a triangle, not because we think aliens build giant triangles in space, but just because it's not a circle. It's just pick something. And what he showed is Kepler could tell the difference. That if there were planet-sized solar panels out there that weren't in a circle, Kepler would not only see them go in front of the star, but they wouldn't make that shape we saw. Remember, it goes down, goes flat, comes up again, and make a different shape, depending on the shape of the object. So this astronomer, Luke Arnold, started thinking they could look like anything. Maybe they'd look like this, and then you'd be able to tell. And you can kind of tell, right? If this goes in front of the star gets a little dimmer, then a little dimmer, then a little dimmer as each of those panels moves in front. And then it would reverse it on the way out. It would have a strange, stepped shape to it. Then he got really creative. Maybe you use these things to send signals, to say, hey, look at our stuff. So here's one thing he imagined. Maybe we'd see something like a planet go by, and then right away we'd see it happen again, but be twice as deep, because there were two of them. And then a beat, and then 3 times as deep, because there's 3 of them. And then a beat, and then 5 times as deep. Well, now we got prime numbers, right? You can say, hey, look at us. We've built these things. And you don't have to send powerful radio signals. Your star is the transmitter. It's kind of a cool idea. I like the paper. It's creative. It was neat. So NASA had accidentally done some SETI for us. Isn't that great? They went looking for planets, and they accidentally built a Dyson sphere hunter. I loved it. Now, obviously, they didn't find a Dyson sphere, or this talk would have had a different title, right? You would have heard about it if we had found Dyson spheres around other stars. So Kepler didn't see anything like that, right? Right? Well, that's actually really hard to say because there's a lot of data. Here's one thing it found. So, again, the star has some brightness that's at 1, and then every now and then it gets dimmer very regularly, like a couple times a day. And this particular star, when it gets dimmer, doesn't always get dimmer by the same amount. So something's going around this star every 10 hours or something like that. But it's not always the same depth, just like Luke Arnold had suggested might happen if they're trying to get our attention. And then if you zoom in and look, like, what is the shape of this thing blocking the starlight? It's not that shape we talked about. It's got this kind of weird, it gets all dimmer and then it slowly fades back up, almost like it's a long triangle or something like that. This was really cool. And I was like, man, like Kepler can find these things, and if this was hiding in there, who knows what other things are in there? Maybe we can't say it didn't find anything. Maybe we have to look harder. And what had happened is that NASA's planet-finding algorithms were only looking for round planets, and they weren't looking for things like this, and that's why it had missed it. And they could still be hiding in there. So what is this thing? We think, and this is work that I do now, we think it's actually a close-in planet like Mercury that's so hot that the rock is evaporating into this cometary tail. And that's what you're seeing. And sometimes the tail's big and sometimes it's small. And so what you're seeing is this cometary tail of rock vapor condensing. And that's why it's not round, because it's not round. It's a cometary tail. It's like a long oblong triangle. And sometimes it's there and sometimes it's not. We don't understand these things very well at all. But that's what Kepler found. Cool. Well, let's keep looking. Here's another star Kepler stared at. That's a weird looking thing, isn't it? Like the star is kind of getting brighter and dimmer, and then it gets a step down, and then down again, and then up, and then up. That's a lot like Luke Arnold said. It would be 1, and then there'd be 2, and then there'd be 1. Here's something else this star did. Over the course of 2 weeks, it slowly got dimmer. And it ultimately got 15% dimmer than it usually was. Remember, planets make things 1% of 1% dimmer. This is 15% dimmer. Whatever's blocking the starlight is like as big as the star. And then it snaps back to its original brightness, like it's a big triangle, like a big star-sized triangle going in front of the star. Like, what is this thing? Here's something else that this same star did while Kepler was staring at it. It got dimmer and then brighter and then dimmer and brighter, then it got really dim and bright. Each of these dimming events is something else passing in front of the star. None of them are round. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9. There's like 20 different things passing in front of the star. So we got really excited. Like, what are we looking at? This is amazing. And then the reason it stops there at day 1580 is that the Kepler spacecraft broke. And so we couldn't get any more data on it. And this is all we had. Super frustrating. So the astronomer in charge of figuring this out, Tabby Boyajian, who's now faculty at Louisiana State, studied this for a long time. They had an internal name for the star. They called it the WTF star, which obviously stands for where's the flux? Where did it go? What happened to this thing? This is a paper they published. All these names here, these are citizen scientists that found it, that actually went looking for things like this in the data and found it. And so what Tabby decided, which was very reasonable, is that the scenario most consistent with the data in hand is the passage of a family of exocomet fragments. That is, imagine you took Pluto and you put it on a big orbit like a comet. You got it really close to the sun. All the ice would evaporate, all the dust would come off, and you'd get a huge star-sized tail. Something that big like Pluto evaporating would do something like this. Now, we have no reason to think objects the size of Pluto have cometary orbits around stars. But it did seem to basically explain what was going on. So that's what she published, and it got a little bit of traction in the media. Pretty cool, right? But one thing Tabby did was she was shopping this around and trying to figure it out, solve the puzzle. And she asked me, oops, what it might be. And I said, I don't have any really good ideas, but I have an interesting idea that goes back to Freeman Dyson. And so we thought that was interesting. She didn't put it in the paper because, it seems kind of out there. We need a little more before we run with it. But one thing we did do is we contacted the people that use the radio telescopes to do SETI and say, you know, it's all about where to look. This is a super interesting star. Why don't you point at that? So we put in time and got time to use the world's largest radio telescope, the Green Bank Telescope in West Virginia, to take a look and see if there were radio waves coming from the star. Now, Ross Anderson is an editor at The Atlantic. He's a journalist. And he was in Washington talking to Andrew about radio waves and looking for life and whether NASA's going to fund it again. And Ross asked Andrew at this dinner, are there any stars you're particularly interested in? And Andrew said, yeah, there's this one really cool star that Tabby Boyajian and Jason Wright asked us to look at. So now the media knows what we're doing. And now we're into, how do you convey uncertainty? Because we haven't found anything yet. We just thought it was cool. We're going to look into it. And out comes a story. Now, Ross Anderson's a great writer, and this is a really good article. I love it. And he interviewed me. And this is something I blurted out in the middle of our very fun interview. It looked like the kind of thing you might expect an alien civilization to build. And that's what got the pull quote on the article, which got millions of reads. And things kind of blew up. BuzzFeed was not as careful as Ross had been. Have we really found an alien megastructure? It's all very hyped and sensationalized. The Daily Mail in the UK completely blew it up. And it was weird for me because my colleagues are now reading in the paper that I think we found aliens, which was an uncomfortable position to be in. Neil deGrasse Tyson, people know Neil. It's often his job to deal with messes like this. Anyway, this was very embarrassing for me. We had to get a paper out. I was like, please stop asking my colleagues what they think of me claiming I found aliens. But what I found was, you know, when I talk to my colleagues, if I'm serious, I write a paper, I explain my thinking, and I get out in front of it and don't let the media run away with it, that they kept respect for me, and that's been very validating. So I should tell you what it turned out to be. All the attention Tabby and I managed to turn into a Kickstarter to try and solve this puzzle, and we actually raised $100,000, which was enough to rent telescope time to monitor this star and see it happen again so we could actually study what was blocking the starlight. And so Tabby and I and an astronomer named Eva Bodman and some others worked very hard to try and figure out what it was. And I believe here we go. And it happened again. The alien megastructure started dimming. Ross helped cover it in the Atlantic. We were all very excited. We got lots and lots of data studying this thing when it finally happened again. And these are the data. The bottom line, I'm not going to walk you through the whole plot, but the bottom line is that whatever was blocking the starlight looked like ordinary dust like you would see in a comet tail. That's what this is telling us, that it was blocking more blue light than red light. That is not what solar panels do. Solar panels catch all the light. But comet tails tend to block more blue light than red light. And that's what we found. And so this turned out to be the right explanation. This particular image is of a rocky planet, but it was an icy planet or something like that. So it looked like Tabby was right. It's a big family of giant comets. But there's another way that we can go about trying to see if there are any of these Dyson spheres out there. How can we find something like this? Well, we don't have to wait for it to block the star's light. If there's stuff near the star, it's going to be hot. So an analogy is I'm out there looking at you, and if you sit really still and don't laugh at any of my jokes, I won't necessarily know that you're a human as opposed to like a crash test dummy with really good makeup or something, right? How could I tell? But if I had some of those heat-sensitive infrared goggles, I could turn them on and look, and the crash test dummies aren't warm. They're room temperature. But all of you are 100-watt heaters. you're warmer than that, and you give off infrared radiation. So in the same way, we can go and look at other stars, and this was Freeman Dyson's original idea, and see if anyone's home. You drive down the street. Who has, put away their home for the season, and it's just sitting there at ambient temperature, and who's home running a fireplace, got the heaters on, doing all of that? Infrared goggles will tell you. We can look at other stars. Here's the Andromeda Galaxy. We can put on our infrared goggles and say, are any of those stars giving off infrared radiation because there's stuff around them that is warm? And this is what happens when you use the Spitzer telescope to look at another galaxy. You see the dust. You see all this dust, but this thing down here at the bottom, the blue blob, that's a galaxy with no dust in it. And it's also not filled with Dyson spheres, because if it were, we'd see the infrared radiation. So looking for infrared radiation was Freeman Dyson's original idea. It's something I've worked on, and actually recently there's been a student in Sweden that's been working on the project as well. And recently we've finally come up with an answer. This student, Matthias Suazo, in Sweden, looked at most of the stars in our part of the galaxy. He put together data from the European Space Agency Gaia mission, from NASA's WISE mission. Here's NASA looking for aliens again, even though it didn't mean to. And all these other surveys. He put all the data together, and he showed it would be, just like Freeman Dyson said, it would be really obvious if there were a Dyson sphere around a star. We'd see it across the galaxy. And he showed there are almost none of them. Virtually none. The vast majority, many nines of stars in the galaxy do not have Dyson spheres. And we didn't know that before. Now we know that. So that's really cool. He then looked at the ones where he wasn't sure, took a careful look, and decided there were 7 that, darn it, really kind of looked like we were looking for. Now again, it's like Tabby star, the wow signal. We don't know what we have. We're not saying we found aliens at all. We're saying if Dyson spheres are out there, these 7 stars are weird enough that they might actually be something like Dyson spheres. So we found 7 candidates. This is a great paper. It's very scientific. We're just moving along. But of course, the press wants to know what's happening. And so you know what happened next. May have found potential evidence for life. Forbes, ET can harness red dwarfs using Dyson spheres. What do we got here? Popular mechanics suggests we found alien civilizations. There's Freeman Dyson, a picture of him. Oh, look at this on technology. What else do we have here? We got a few more. NBC News ran a whole thing on it. I don't know if you saw them talking about it on the air. So it's an ongoing fight to try and explain that we haven't found aliens. We really don't have good evidence for it. But it's a really exciting time to go looking for it. And it's a really exciting time to be doing things other than just radio waves. And so that's what we do at the Penn State Extraterrestrial Intelligence Center. I feel really lucky to be able to work on this, to train students to work on this, to get PhDs in this kind of stuff. At Penn State, we're really trying to broaden the whole field to train people, because when NASA won't fund it, it's hard to train students in it, to look beyond just the radio, to look for things like Dyson spheres. You're gonna get through this whole thing, it's gonna work. Almost there. We foster a whole community. In fact, right now, today, junior researchers in the field are all gathered at Green Bank, reproducing that original meeting that Frank Drake had with the Drake equation. They're meeting there to form their own community of SETI practitioners. And I hope that someday I'll be able to give this talk with a different title, that we finally found that there's intelligent life in the universe. Thank you.
So I've read a lot about how big the universe is.
Yeah.
Where is our seat in the universe? Are we in the middle? Are we in one far end? How do we tell how close our nearest alien neighbor might be?
That's a good question. So the universe is really big, and it might go on forever. Also, when you try to look at the edges of the universe, not only are things so far away, it's almost impossible to understand what you're seeing. We're also seeing it from a very long time ago, and so if you look at stuff at the edge of the universe, you're looking at stars that are so young and things that we might not expect life have had even a chance to form yet on those very young things. It's much more practical to look in the galaxy. The Milky Way galaxy is, unfathomably huge, but it is just our little corner. And I say corner, there are no corners to the universe. There's no center or corner. It goes on forever. But our little spot. And we can reasonably detect powerful radio transmissions or Dyson spheres across our galaxy. It's kind of a good size. We can find planets around the very closest stars in the galaxy. So if you had a big picture of the galaxy, like right there, that's where we can find planets that we could study for life. So in the galaxy, we're kind of halfway out. So the galaxy has about the dimension of like an LP vinyl. It's about those dimensions. And so you listen to it for about halfway through the record, and that's where Earth is, where the needle is, right then. There are more stars in the middle, but some people think that's a bad place for life. Fewer stars on the outside, but some people think that's a bad place for life. We might be in the sweet spot, we don't know. So we try to look in the galaxy.
Next question is back here.
Hi, I just finished reading an interesting book called The Swarm by Frank Schatzing, okay? So what comes to my mind is, are we looking for something, you mentioned it earlier, that we're looking for something from our perspective, that intelligent signs of life could build the sphere, or intelligent existence is going to mimic something like us because it's going to be that far away from its sun with the planetary conditions, etc. Or is our hubris coming from our perspective as humans, thinking, just like we think God is a human, you know, if there's such a thing, God is a human, that extraterrestrial life is going to be able to build this or look at our radio waves, and not maybe amoeba, or look at the cockroach or some of the forms of life that have lived longer than human life that we think is the ultimate, penultimate intelligence. But we might just be a fungal blip. You know, we're gonna perish because look what we're doing to the Earth. And these other species have existed longer. So your search, where is it open for that kind of looking? Or are we looking for something because your premise is that you're going to look for a planet that's the same distance from the sun, that's going to have the same climate, that then would foster the same type of life?
That's right. It's a really hard balance because we know the aliens will be alien, right? They're not just going to be people with face paint. They'll be really alien, and they might communicate or build things and do things in ways that don't make any sense to us at all. And so we need to be open-minded and look for any kind of technology. And so one search strategy is to just look at everything for anything weird, right? And try not to bias ourselves in a certain direction. But looking for anything weird anywhere, that's a challenging search strategy. The other way we can do it is try and guess what things we do will be common. Like if you want to communicate among the planets, you don't have many options. You could use radio, you could use lasers, but you know, there's only so many forces of nature. There's only so many ways to do that communication. And so we're pretty confident there are certain things that any spacefaring species would do, but again, could be wrong. And so we try to keep an open mind. So it's a hard balance between looking for things that do what we do and looking for anything weird. Do you do a targeted search where you think you'll find things? You mentioned it, that distance from the star. Do you want planets that are right there because it could have formed life? Or should we stay more open-minded and just look everywhere? So different people advocate for different strategies, and that's why I think we need a broad portfolio.
Okay, over here.
Would you address the UFOs and the transparency that the government has supposedly given to some of the UFO sightings?
Yeah, so I'm an astronomer, and I look for stuff far away, and I am not an expert on UFOs. It's totally outside my training. I mean, obviously I have to be aware of stuff that's going on with UFO, this and that. You know, if there's intelligent life out there doing something we can find with our telescopes, I'm an expert and we can look for those things. Personally, as a non-expert, I don't know anything about, you know, aircraft and radars and, you know, how people see things and all of that stuff. I've never seen anything out of the UFO community that's made me go, maybe I'm looking in the wrong place. That's just my bias, though, and I'm not an expert. So it's not what I do.
This side of the room.
I've heard people say that we've sent so many satellites up into space that we're trashing space, and so my question is, do we have a Dyson sphere?
Do we have our own Dyson sphere? Yeah, we have our own little baby Dyson sphere, sort of. It's very, very, very small, and there's no way you would be able to detect it. I mean, it's hard to even detect our satellites from Earth, much less from another star. So when we think about what a Dyson sphere is, I mean, you have to scale up what we've done tremendously by like a factor of 1 billion or something like that. It's really large. But yes, I think the fact that we have sent these things out is sort of a proof of concept that it's a very natural thing to do. We aren't trying to build a giant structure around the sun, right? No one's like, let's build a Dyson sphere. It's the kind of thing that happens. Just like, you know, no one said, let's build all of New York City with these 5 boroughs and these buildings, right? It just kind of grows on its own because there's more land, there's more stuff you want to do, and it gets bigger. So yeah, I do think we have a tiny one. As for crowding space, fortunately, that's mostly just around the closest parts to the Earth, and the atmosphere drags most of those down in the long run. So but it is becoming a problem, you're right, that we have too many satellites in low Earth orbit. It's a huge problem for astronomy. It gets in the way of all of our measurements. It's almost a disaster, actually.
Do you have an alternative model for DNA, and what would you accept as life?
Well, oh my goodness. Again, I'm no biologist. Looking for technology is neat because radio waves, whoever built that radio telescope is kind of independent of what the builders looked like, right? They could look like ET or the xenomorph or like us or, you know, like just blobs of whatever. Radio waves are radio waves. And so one of the nice things about looking for technology is I don't have to address questions like, what is life? People talk about maybe it's going to be post-biological life. Maybe most of the life in the galaxy is robotic, and it's all computers with artificial intelligence. That's fine. I'll see their radio waves just as well. As for what is life and stuff, I don't know. There's a lot of definitions. I think if it's self-sustaining, it can reproduce, and it can go gather resources to continue itself reproducing, manipulate energy and matter, build things. That's intelligent life to me. And so that's all I need for my definition to go find them. I really try to stay within my expertise and not claim to know things that I have no training in.
We're back here.
Einstein apparently theorized about the theory of portals. In astronomy, looking into space, have they ever seen anything that would indicate that possibility as a reality?
Of portals. I don't think so. I think this has something to do with like UFOs and.
No.
No. I don't know what you mean by portals.
Might have something to do with them, but you've never seen anything visual things in space that are not solid, which would indicate space and time warps.
No.
Okay.
That's right. We've never seen the indications of space-time warpage that we see in space are both pretty well understood according to Einstein's gravity and extremely subtle. In fact, the first time we actually saw them happen, it almost immediately won a Nobel Prize a few years ago. So it's a big deal when we look, but we haven't seen anything like that.
Are we sending out signals?
Yes.
That we're expecting something back? And if so, where are they being sent to?
So we send a lot of radio signals out. I mean, you know, our Wi-Fi signals go into space. Our TV signals go into space. Radio waves go into space. Earth has been advertising that it has life on it for billions of years because life has altered our atmosphere in ways that only life can. So if there are alien species out there with big telescopes, they would have noticed 1 billion years ago that Earth is the kind of place that might have life. And for the last, say, 60 years, our radio waves have gone out. And so any star within 60 light years, in principle, with a big enough telescope, might notice that we have radio transmitters. And that's a lot of stars in that sphere. I mean, compared to the galaxy, it's like a little tiny speck. So most of the galaxy doesn't know about our technology. Most of those signals are pretty weak, going out in all directions. Every now and then, we send a big old blast for a few minutes, mostly when we're trying to get radar ranging to asteroids to see if they're going to hit the Earth in the future. We do radar really powerful, and that's a big blast. And when we talk to our spacecraft, we send a pretty powerful directed signal. It's very hard to communicate with the Voyager spacecraft out, 100 times the Earth-Sun distance away and have it hear us. So we do short, brief, highly targeted things that could be detected across the galaxy. Eventually, they have to get there first. And then we send weaker stuff in all directions that would be harder to detect. As for a response, who knows? The premise, I'm going to spoil a little bit of contact for you, but the premise is that as soon as our radio waves get to a particular star, they send back a response. And so that's an old idea that it could be. We could trigger a response just from I Love Lucy.
Okay, over here.
Yeah, this is sort of two parts. Excuse me. One is, so there's a term in the Drake equation where you go from, say, this life, meaning like a virus or something, to intelligent life.
Yeah, it's a big jump.
And what, so that's a big step.
Yeah.
So what is the number that people are throwing in for that these days?
Yeah, that's interesting. And I've been trying to learn the evolutionary biology here about how likely that might be. And at the Green Bank workshop where they wrote that down, the biologists, including Nobel Prize winners, so they thought it was very likely that evolution is so powerful that if life gets started, it will always become more complex, and then it seemed to them inevitable that eventually intelligence would develop. One check we can do is, you want to know, was it some random freak event that most planets have pond scum and stuff, but no animals? And that there was some weird, incredibly unlikely evolutionary leap that led to Earth getting animals, and then animals eventually getting human-like intelligence? Are any of those hard steps? What's interesting is that once you have animals, intelligence like humans is not some super incredibly rare event. Just about every aspect of human intelligence can be found elsewhere in the animal kingdom. We have a particular constellation of intellectual traits that lets us build, buildings and rocket ships. But individually, all the things we do, how we're social, how we communicate, how we transmit information, how we have a sense of self, how we can think about and plan into the future, how we can abstract into numbers, all of those things exist piecemeal in the animal kingdom, including among animals that we don't share evolutionary descent of a brain from. So the octopus independently developed brains, cognition, communication, all of these things completely independently of humans and our line. So we think once you get neurons, intelligence is probably going to happen because it's happened so many times on Earth. Now, maybe neurons were special, maybe big animals are special, that's a little more unclear, and it's still an area of active debate among biologists. So optimistically, I like to think that term is one, but it could be 1 in a billion. We really don't know.
Well, so just given that then your answer says there's probably some very smart aliens out there, do we really want them to know where we are? And
like I said, they know,
do you want them to show up? They probably want something.
That is definitely the plot in science fiction because we need to write a plot, right? We have to interact with them. You take a screenwriting class or a fiction class, and your coaches, they read the plot, they're like, this is very boring, where's the conflict? What is the conflict that's going to get resolved? Because if there's no conflict in the story, no one watches it. No one reads it, and you don't hear about it. So by definition, all science fiction has conflict in it. And since it's often about aliens, it's about conflict with aliens. And so we're primed from science fiction to expect that we will have conflict with them when we come in contact with them. And we need to recognize the reason we expect that is because every story we've heard about them is about conflict. And there's no actual reason to think that's the case, that they will necessarily conflict. Most species out in nature, when they cross paths, don't immediately start killing each other, right? There are some predators out there, sure. But most species just totally ignore each other. And so we really don't know, and I try to keep an open mind about it. But like I said, if they've got technology and telescopes, they've known Earth has had life on it for 1 billion years now. And so I don't think our puny little radio waves are going to trigger the invasion or the armada or whatever. That's great science fiction, but I don't see any reason why that would be what really happens. Life is usually more boring than a science fiction story.
And we're going to have a question now from our online audience.
Great.
The question is, with all the advances in AI, as you project further advances in AI, is that going to assist in the process of search?
Yes, for sure. What we call artificial intelligence right now, one part of it, this machine learning we can do, that has generated, ChatGPT and all of these things. What it's very good at doing is stereotyping. You give it a ton of pictures, and it learns to stereotype, oh, this is what a whatever looks like. This is what a lemon looks like. This is what a cat looks like. And they're really good at it. And you can ask them to generate a new picture of a cat that it's never seen before, and it'll just draw a stereotypical cat. And that's super powerful because they can take huge amounts of astronomical data and start to stereotype stars. Oh, that's what a young star looks like. That's an ordinary star. That's a whatever star. And once it gets good at that, then it can go through and it'll every now and then go, well, that's not a star. That doesn't look anything like a star. And then we're like, ooh, let me see that one, something weird. Right? And that's really powerful. That's getting back to this earlier question. Maybe we're looking for the wrong thing. Maybe we shouldn't look for what we expect, but for something odd. And what's powerful is we have terabytes, petabytes of data coming in from NASA and National Science Foundation experiments, all this data. And artificial intelligence can say, this is the ordinary astrophysics, and this is the weird stuff that maybe the SETI people need to look at. I'm very excited about this prospect.
All right, here in front.
This kind of puts you on the spot just a little bit.
That's where I am.
With all of the numbers, all of the exoplanets,
yeah.
Do you believe that there's a high probability of intelligent life out there?
Yeah. I'm going to be absolutely honest, I really don't know. Some days I'm like, we are just a fluke. Or yeah, there's a lot of life out there, but none of them think radio waves are interesting. They just all, do whatever they do all day, I don't know, building pyramids or watching cat videos or something, and they just never do anything that we would ever notice. And then other days, I just think about the numbers, and I think they've probably already filled the galaxy. There's probably one in the next one over, and we just haven't found the right frequency. What's great is that if we're doing this systematically and scientifically, then we have to just get rid of our biases, ask what the question is, and go about it without any expectations. And I've practiced that so much that I've started to really believe it. So I really don't know. If I didn't think it was likely, I wouldn't be looking, though. So it's definitely not, I definitely don't think they're not there.
Back here.
This may be a little too personal, but I'm curious, how does religion fit into this with your children?
With my children?
Yeah, how do you explain what you're doing and take into consideration some of the religious teachings?
Yeah. So two separate questions. My kids think it's really cool. They know I look for aliens, and my daughter wants to be an astronomer. It's adorable. The religious angle is super interesting, and I thought I knew the answer to that question until I started talking to some philosophers and some anthropologists, and realized that my idea of how religion would react to the discovery of life out there came from science fiction and conflict, and it was totally wrong. So Bruno got burned at the stake for the plurality of worlds heresy. Uh-oh. It's not mine. It's not mine. All right, thank you. Religion, right. And so for a while, the Catholic Church was very orthodox about how there could not be alien life out there. And they were getting deep into the philosophical weeds about if Christ died for man's salvation and Eden was the special point of creation, then there couldn't be a second Eden, or then you'd have to have a second salvation and a second Christ, and that violates this verse, and it was all very theological. But the truth is today, the Catholic Church is way more chill about, the Earth going around the sun, and even the possibility of intelligent life out there. The Vatican astronomer he gets asked this question all the time, and people are expecting him to have strong opinions, and he's like, that'd be cool. We have a lot of questions I want to ask the aliens about all this stuff. There was a study that was done asking people how they thought the world's major religions would react to the discovery of intelligent life in the universe. And there was a pretty good consensus. People felt that other people's religions would not be able to handle it. But when you ask them about their own faith, they're like, oh no, that'd be fine. I wouldn't care. And the really religious people were the ones that were like, no, that's cool. The people that were most worried about religious people freaking out were the atheists. But all the religious people were like, it's fine. And so I was surprised to learn that. It was a tiny study. But I don't think mainstream religious reactions are a big problem. Now, cults are a different matter. Remember the Heaven's Gate cult? There will definitely be people that freak out along a religious dimension, but it won't be people, in mainstream religions. It'll be people that are being convinced to do horrible things and culty stuff. So I think we will have a problem with the cults.
All right here.
If we could circle back to the Drake equation at the very beginning, and I don't remember how many terms there were, but you said there were about at least two of the terms, there's reasonable ideas about the values for them. So if you were to plug in best guess for the bright people like yourself, what would the numbers come out to be at the end for the chances of life elsewhere, just in our galaxy?
Yeah. So one thing I didn't mention about the Drake equation is that it's super conservative. And the reason is it only counts species that are on their home planet. And it assumes that at some point they stop transmitting for some reason. But there's no reason that humans will necessarily forget how to transmit radio waves, ever. Like, even a nuclear holocaust on Earth doesn't make humanity go extinct. Like, maybe for thousands of years we're, hunter-gatherers or whatever, but we're still modern humans, right? There are still libraries. It won't take us as long to come back a second time. And so it's not obvious to me what stops us long run over the future of the Earth from transmitting. So L, that last term, could be very large. The second thing is we can spread. N for the solar system, you think it's 1, right? We're here, there's no other aliens, there's no other planets, right, giving off radio waves, but that's wrong. Mars is crawling with robots that are sending out radio waves. Mars has technosignatures that are detectable from Earth. If you point a radio telescope at Mars, you can't miss them. But it doesn't have any biosignatures. It doesn't seem to have any other life on it. And so already we are spreading our radio signals across the solar system. And if you give us millions of years, why not the galaxy? And so the Drake equation only counts Earth. It misses all of the spreading. That is at the heart of the Fermi paradox. But to answer your question, the most pessimistic numbers are less than 1 in the galaxy. If you think, for instance, that the development of the neuron or the development of animals, whatever, analog of animals might exist out there, is so rare that it was a fluke here, you can easily get numbers that say there are none in the galaxy. With those two numbers now being locked in at pretty high values, I think most people kind of get somewhere between, I don't know, like 100 in the galaxy and millions in the galaxy, which means that our, the nearest example could be quite close.
Back here.
Thank you, Jason. Well, how much more powerful will the next generation of telescopes be?
So in the radio, the big project is called the Square Kilometer Array. And back when they were thinking, NASA was thinking about how to search the whole sky at every frequency, they pioneered this idea that you would just fill an enormous area of land, just fill it with telescopes. And in fact, a whole square kilometer, right? Imagine like a square mile that's just all radio telescopes. So that idea's been around for a long time, and it's actually getting realized across the southern hemisphere, in Australia and South Africa especially. They're not putting them all together in one field, they're spreading them out. It turns out that's better. And they're not huge telescopes, they're all pretty small as radio telescopes go, but the total collecting area is going to be a square kilometer. And the big problem there is the computational power needed to analyze all that data, but we're getting to the point where it's possible. So at some point in the next 20 years, the prototypes that are being built will hopefully get fleshed out, and that will be the most powerful radio telescope. The numbers are a little hard to work out, and it's uncertain, but it's going to be close, that telescope is powerful enough that if a planet like Earth is around the nearest star with aircraft radar and all the stuff we do, that it might be able to detect that kind of passive leaked transmission. We don't need them to be getting our attention. We'll just notice them going about their day, which would be pretty amazing.
We have one more from our online audience, and we have time for just a couple more here.
There's been a lot of discussion about water being an important determinant. Why is only water, such a determinant? And in the next 10, 20 years, what's going to be able to discover water?
Yeah. A lot of thought has gone into life as we don't know it. And people have tried to figure out how to get biochemistries that don't rely on water. The problem is, first of all, water is really common in the universe. It's just oxygen and hydrogen, two of the most abundant elements. And so we expect water to actually be everywhere. All the icy moons and Enceladus and Europa, water's everywhere. It's a great solvent, and it's polar, and the biochemists tell me that when you put all that stuff together, it just allows for fantastically complex chemistry to happen of the kind that led to DNA and stuff like that. Which is not to say it's impossible to do in any other solvent, but other solvents are super rare. And so there's been some work, maybe liquid methane could do it, so maybe we'll find life on Titan that's made out of basically natural gas, right? That's a liquid. Maybe it can form in there. But when you work it out, it just doesn't seem to be as rich. So I think it's very reasonable to look for water. It happened here, so we've got that. It's super common, and it doesn't necessarily assume it'll be DNA and carbon stuff like ours. It could be some other way of doing it. So again, you have to balance between, do you look for what you know, or do you just look for anything weird? And I think you should do both.
Okay, back here.
Thank you. You're looking at an energy source. There are other energy sources out there. Are you looking at any of those?
You mean other than stars?
Mm-hmm. Black holes, dark energy.
Mm-hmm. Yeah. So I thought about dark energy and dark matter. The problem is it's too diffuse. It's just, starlight is much more concentrated. Even when you're out among the stars, it's more concentrated. Just all, the night sky, all that starlight falling on you, that's more energy than the dark energy and dark matter that fills the universe. Stars are just generating huge amounts of energy and sending it off into space for free. And so it's just lying around to be gathered. It really does seem like it's the most likely. Now, black holes are interesting. If material falls into a black hole, it heats up, it radiates, and you get all this energy out. And that turns out to be an extremely efficient way to generate energy from mass, much more efficient than stars. So black holes are, I would say, the only other good source of energy on big scales that we can see across the galaxy, and we've thought about that. They're also really rare, though. There aren't very many black holes compared to stars. We have 200 billion stars in the galaxy, and black holes that are generating energy, it's much smaller than that. So some people want to focus on the center of the galaxy where we have a supermassive black hole. That's cool. And then there are some others, and we think about black holes as a potential source as well. But those are the two biggies, and after that, I don't know, you're scraping by on so little energy. Why wouldn't you just take the starlight that's around you for free? That's my philosophy.
All right, to finish this up, one more thought. If there's anything coming up in the next 5 years in this field, what are you most excited about?
I'm going to add something at the end before I go, but the next 5 years, yeah. So I like to tell my students that there are sort of 5 big ways to look for aliens that seem to have a lot of promise. And I hope my students come up with 5 more in the next 5 years, but I don't know what those will be. You can look for radio waves. We're doing well on that. You can look for optical and laser signals. I think that's very promising, and there's a big new project going on in UC San Diego called SETI to look for those things all over the sky. I think that's going to revolutionize that particular one. We can look for Dyson spheres. I'm working on that. We can look in the solar system to see if the Bracewell probes are here. I think we've got a good way to do that with the new surveys, and I have a student working on that I'm very proud of. And then we can look for things in other planets. So when we're going to be soon, NASA's launching a telescope in the next 40 years or so called Habitable Worlds Observatory that will actually take images of planets that might be like the Earth to study them to see if they have life. But what if instead of finding, methane and ozone in the atmosphere, they see CFCs, chlorofluorocarbons? What if we see obviously artificial chemistry going on in their atmosphere, like we do in our atmosphere? That's not impossible. We might see something like that. So we might find intelligent life that way as well. So those are those timescales. Yeah.
All right. Do you want to close us out?
Oh, one last thing. The books, my wife's books. My kids are 10 and 14, and when they were little, my wife started, thinking. It started with "Twinkle Twinkle Little Star," and we hated that song. Hated that song. Because the next line is, "How I wonder what you are." And I'm like, well, yeah, but I mean, not the way you mean it. Like, I teach my grad students how incredibly well we know what stars are. So Julia rewrote the lyrics from an astrophysicist's perspective. And so in addition to the board books out there, which are great, she also has a picture book for nighttime reading called "Twinkle Twinkle Little Star, I Know Exactly What You Are." That's actually my favorite of the three. And so there's a link, I think, on the announcement where you can find that one as well. It's beautifully illustrated, so please take a look at that one as well.
Yep, the link is on the program page for this event on our website at vailsymposium.org. Please join me in thanking Dr. Jason Wright.